and for dynamic characteristics, we need to know the transfer function of it. So that's what I said. And I say that instrument could be zero order, which is a very, very interesting and ideal instrument. And if any instrument exists which order is zero, we always take that instrument because there is no dynamics, no lag, no delay, and no distortion. Whatever is the input, immediately output, it will be reflected, only multiplied by some gain. And I told that the potentiometer is an ideal example of a zero order instrument. So with the potentiometer, if you measure the displacement, then that displacement measuring device will become a zero order instrument. Now, I said that for a first order instrument, there are two parameters. One is gain parameter K, which is called static gain, and there is another parameter which is called rise, which is called time constant tau. So the transfer function is K by 1 plus S tau into Qi. So, and that is a first order instrument. And I said that a thermometer could be a first order instrument. And I gave a reason which is quite vague. I say that when you keep this thermometer in touch with a with some temperature, then thermometer gradually rises and settle to a steady state point. So now can you see my screen? See, you don't respond. So I am asking, can you see my screen? Nobody is responding.
Yes,
How do I know that whether you can see or you cannot see? So I wait. Either you respond, then I will proceed. Then I sit. Otherwise, I will sit here. I shared the screen. So can you see it?
So screen is visible.
So I shared the screen. Can you see it?
Yes, sir.
Okay. Okay, fine. Then let's proceed. So I did not share any presentation. So I was just speaking. So if you hear that, that is sufficient. So the point what I was trying to tell that about the zero order instrument I told, and the first order instrument I said that the example is thermometer, and I said the reason like this, that if you put the thermometer with the temperature, thermometer mercury will rise gradually, slowly, and then it will stable or at some point, and that will reach the steady state. It will no longer rise, and that is the temperature we measure. And I said that might be the reason for it is a first order instrument. But as you later you also see that in second order instrument under such condition, for example, if it is a critically damped or it is a over damped, it may go on increasing and it may reach to steady state. So whatever the reason I gave, it is a very vague reason, and that reason cannot be a very strong reason for thermometer being a first order instrument. So to know whether the thermometer is a first order instrument or some other or higher order instrument, definitely it is not zero order instrument. There is some delay and distortion associated with that. So to know that what is the order, you need to calculate mathematically the transfer function from the law of physics. So if you start doing this, let's do it now. And we are now probably we can see this, and we are following the book Doeblin where they have derived the transfer function. So here left hand side, if you see, we have a thermometer, we have a liquid whose temperature is Ti, small t, that means it's changing with time, and Ti, I call that the input temperature. And once it is thermometer is immersed in the liquid, then the capillary rises and displacement is x0. And so the x0 is the, so when thermometer is not inside the liquid, so the x0 equals to 0 at 0 degrees centigrade. And when it immersed in the liquid, so the small x0 is the displacement from the reference mark, which is x0 equals to 0. So we assume Ti is the input temperature, that means temperature of the measurand. TTF is the temperature of the fluid, in bulb. Okay, so there are some fluid in bulb. It may be mercury, it may be something else. So that is the TTF. KEX is the differential expansion coefficient of thermometer bulb and the glass, and VB is the volume of the bulb. AC is the cross sectional area or the of the capillary tube. So the displacement x0 will be E, that means differential expansion coefficient between the thermometer fluid and the bulb. VB, that means volume of the bulb, that means the amount of liquid in the bulb. And then AC is area in bulb. So x0 represents the displacement through the capillary tube. So this is obvious. This is a very 3.133 is a very standard equation. Now, if we want to go ahead to calculate the transfer function of it, that means the input temperature versus the output displacement x0. What we can do, we can say that the heat conservation, that means heat in minus heat out, will be equals to energy stored. So we assume there is no heat loss. So heat out is 0. Heat in, we say that it is U ABTI minus TTF. What is the U? U is the overall heat transfer coefficient across the bulb wall, and AB is the heat transfer area of the bulb. Okay, rho. So if you see that UAB, so heat transfer coefficient multiplied by the area into multiplied with the temperature difference. TI is output, TTF is the bulb temperature, will be equals to VB rho C. VB, we have seen VB is the volume of the bulb, rho is the mass density of the thermometer fluid, C is the specific heat of the thermometer fluid, and TTF is the thermometer temperature of the liquid inside the bulb. Now if we see, so this is the 3.134 is kind of governing equation. So in that case we have assumed many assumptions, which is quite valid if we go for modeling the thermometer. So the bulb wall and the fluid films on each sides are pure resistance to heat transfer, and there is no heat storage capacity for both the fluid films and the bulb wall. So this we assume, although it is not 100% correct. Bulb wall may have some heat storage capacity, but we assume that there is no heat storage capacity. The overall coefficient of U is constant. So it may happen that this coefficient U may vary with time, but we are assuming it is a constant. The heat transfer area AB is constant, so that is our assumption, because with the temperature, the area of the bulb may change slightly, and for that the heat transfer area may change slightly, but that is negligible. As transfer area A is constant, and the bulb by conduction or something else, heat loss will be very small from the, although it is the stem of the thermometer is outside the fluid, and some heat may lose from the glass and so on by means of conduction, but we assume that there is no heat loss. The mass of the fluid of the bulb is constant, that is what we assume. It is quite obvious. So, and the specific heat is also constant, it does not depend on the time, and so on. So with those kind of assumptions, what we get this equation VB rho C dTF by dt plus UAB TTF will be equals to UAB TI. Okay, so and this, from this equation, if we use that the equation 3.133, and we divide it, we'll get some kind of equation of 3.136. And from here you will see it is a first order differential equation. And if you divide it by means of UABAC KEX by KEX VB, so you will see there will be again K, which will be KEX VB by AC, because you see that other things will cancel out, and then there will be a tau which will be rho C will be there, and then AC will cancel out, by AB will come, and KEX will cancel out, U will come on the denominator. So our instrument means thermometer becomes a first order. When we model it, it becomes a first order instrument, and the gain or the static gain depends on KEX VB by AC, and the tau, that means the time constant, will be rho C VB by UAB. Now you see, yesterday I was telling that you need to design in such a way that the time constant will be high, and the gain also should be quite high, so that the sensitivity is high, response time is low. That is what we desire. Now if you see, so what is our then first order equation becomes? It becomes tau d or s plus 1 k by tau s plus 1. So now from here, if you see that we want to minimize the tau, so in that case, if we minimize the rho, or if we so here, if you see that, you see the figure 3.35, second figure. So for small tau, it rises very quickly, and for large tau, it rises very slowly. So we want response time to be less, so that quickly it reaches to the steady state for a step input. So we want small tau, and we want gain is high, so that the small change in temperature or small change can be detected. So we want K is very high. So if we want K is high, then we can choose KEX VB, the volume, such a way that large volume AC, that means the area that is less, so K will become high. And for tau, if we can choose the rho, higher rho C, so the C is the specific heat, so it depends on fluid characteristics. VB, the volume, high volume, and then so by choosing all those parameters mean ultimately the nature of the fluid, ultimately the nature of the container of the fluid, volume of the bulb, surface area of the bulb. So we can choose all those things in such a way so that the tau is maximum, so that the rise time is less, and K, static sensitivity, is high. So while we design any instrument, so we first do the transfer function, and from the transfer function we see what are the parameters we should optimize, and based on that, what are the different physical things we should take. For example, second order system, it might be spring constant, it might be damper, so that we can choose all those things properly to get a realistic and proper, sensitive and responsive instrument. Okay, so now tell me if you have any query. Any query up to this point? So if we can say that now it is properly, you can say that thermometer is a first order instrument, because if we derive it, its transfer function is a first order differential equation, and we know that the gain and the time constant, and by selecting the different parameters, such as the the volume of the bulb, the liquid inside the bulb, the specific heat of the liquid, the area of the volume, surface area, and the volume of the bulb, all those things, capillary length. If we choose properly, we can have good sensitive and more responsive instrument. In such a way, you should design an instrument. Okay, so if there is no query, let's move to the next part. So here now I was saying that for any instrument, we have a transfer function, and that can be achieved by modeling the instrument using the law, physical law or law of physics. And then after we receive the transfer function, so that we know the instrument properly. Now the point is, if some input is given to that instrument, we'll get the output, and the output will vary with time. So what will be the output? How we can decide it? So mathematically, if we know the transfer function, it will not be very difficult to decide what will be the output. For example, if you know the transfer function and if you know the input, so you give that input or transform it into the Laplace domain and then multiply it with the transfer function of an instrument, you will get the overall transfer function, overall thing in S domain, and then you take the Laplace inverse, you will get the time domain response that you can easily write or draw the figure. Another way of doing it, which is very complicated way, that you can convolute the time domain transfer function of the instrument and the time domain input, so that you will get time domain output. But that is quite tedious and nobody does. So if you want to go, so now the input of any device may not be a very standard one. So standard one, I mean to say, there are some standard input. Whenever some instrument transfer function we design, we used to give those standard input, and we used to see that, like to see that what will be the output. But when it goes to the field, those standard inputs will not come, or very rarely come. Some arbitrary input will come, time varying input, and accordingly the output will receive. But still, it is very important to know what will be the output, how the response will be, or the system will behave in presence of the standard input. So standard input means there are a few standard inputs. For example, step input is a standard input, ramp input is a standard input, impulse input is a standard input, and sinusoidal input is a standard input. So whenever we use an instrument or design an instrument, we try to characterize the instrument with these standard input, and when it is done, we get some sense about the instrument. We design the transfer function of it, and then we use that instrument in the field. So now let's come to the step response. So first order system, first order instrument, the you know that the dynamic equation or the differential equation is tau ds dt or dq0 dt, the way we are writing, plus q0 will be equals to k qis. So qis is the step input. So at time equals to 0, the input becomes qis. When time is less than 0, the input is 0. So now our objective is to solve this differential equation 3.139 to know the output. So there are many ways we can solve. We can solve by means of Laplace transform or Laplace inverse. We can write QIS is the step input, so it is 1 by S, and then multiply it. So Q0, so K by S into tau S plus 1, and then we take the Laplace inverse, and we'll know what the time response is. We can solve this differential equation in time domain. So if we solve the time domain differential equation, you have seen that right hand side is not 0. So there may be some complementary function or complementary solution, and there may be some particular solution. So when there is right hand side is not 0, so we need to get these two types of solution, particular solution and complementary solution, and then the overall solution will be sum of these two. So if you see that complementary function will be c e to the power minus t by tau, and the particular solution will be KIS. So when we add these two, the complete solution will be C e to the power minus t by tau plus K QIS. QIS is the input. Now you see, as so here the constant C is a constant, and C, the values of C can be determined by using the boundary condition, and it is a differential equation. So if we apply a boundary condition that when t tends to infinity, then Q0 will be QIS, or when t tends to 0, that is at time starting at 0, the output Q0 will be equals to 0. So let's put that value in 3.142. So 0 will be equals to C e to the power 0, that means 1, C plus K QIS, and from there we know that C will become minus K QIS. So if we substitute C in equation 3.142, so the Q0 will become K QIS So C is the minus KQIS plus KQIS. So if I take KQIS out, what will get 1 plus e to the power minus t by tau. So from here you see when t equals to 0, definitely the output will be equals to 0 because 1 minus 1 will be equals to 0. When t is infinity, so e to the power 1 by e to the power infinity, which is 1 by infinity, so which is 0, so output Q0 will be KQIS. Then you see why the K is known as the static sensitivity, because the output will be some multiplying factor into the input at steady state. That means K tends to infinity. That is what this K is known as the um, static sensitivity or static gain. So this way we can characterize, or we can find out the step response of a fast order system. Now what will be the measurement error? So measurement error will be the output minus input. So output is Q0, input is Qi. So we can write Qi minus Q0. But here you have to be very cautious because we cannot write directly Qi minus Q0 because there is a gain associated with it. So output, there is a gain, the static gain, which is K. So we have to divide the output by the gain. So the error will be Qi minus Q0 by K. So then EM will be QIS minus Q0 by K will be equals to QIS into 1 minus e to the power minus t by tau. So now here you see that at t tends to infinity, that the last term will be QIS, so EM will be equals to 0. So at steady state, what if I ask what is the steady state error for a first order instrument? Um, so you must say it is 0 because you can derive in this way, and ultimately we will see you can substitute it this t infinity, and you can get the EM equals to 0. Let me see. Is there any query up to this point? There is no query. If you have any query, you can ask. Okay, if there is no query, I can do. So it is very, sometimes we used to ask in exam that what will be the measurement error at steady state. So people used to do that time domain output and minus the time domain input and difference, and then t tends to infinity, and that will become the steady state error. Now if that same thing can be done in Laplace domain. So because you know that the final value theorem, so t tends to infinity, En or error will be same as 1 by s into Es, which is in when s tends to 0. So in Laplace domain you can also calculate the error because output you can calculate in the Laplace domain. Input, you know, for example here the input is 1 by s, output is 1 by s into tau s plus 1, and then both you can subtract, you will get the input minus output, and then the error will be limit s tends to 0 s es, capital Es, that means the error function in Laplace domain. And if you calculate that, you can find out the error, steady state error, very quickly, and that will be more easier way to find out compared to the time domain response. Okay, so any query? Okay, so nobody is asking anything. So, okay, so let's proceed now. So this is the step input of a first order system. Now, what will be the ramp response of a first order system? So you know what is the ramp signal from signals. So ramp signal is a signal which is increasing its magnitude constantly with time. So if you draw it, it will be kind of straight line when you draw input versus temperature, input versus time. So this one, first figure, you see time versus input, it is a kind of straight line. So at t equals to 0, the input will be 0. When gradually the time will increase, the input will keep on increasing. That is called the ramp input. All of us know that. So to apply a ramp input to a first order system, we assume that initially the system is in equilibrium. That means Qi is 0, Q0 is 0. So both are at 0 condition. So at t equals to 0, the Qi suddenly starts increasing. So we can write that Qi such as if t less than 0, Qi equals to 0. If t is greater than 0, Qi equals to Qis dot t. Okay, so you see here, so QIS dot is a some constant value and that into t. Basically, this constant value is the slope. So if it is 1, it will write the, so Qi will be equals to T. That means it will write with the 45 degree will be the angle between time and the input. It might be differently. So to incorporate that, QIS dot is added. You can assume it is a constant value instead of QIS dot. That is perfectly fine. Sometimes if you write QIS dot, it is misleading. You can think that this QIS dot is a constant value. So you can see that tau d plus 1 into Q0 will be equals to K QIS dot T. And this is the governing equation. Now this equation you can solve either in time domain or in the frequency domain or Laplace domain. So you can solve it, suppose you solve it in the time domain, so you have both the complementary function and particular. So you will get that QOC, which is C to the power minus T by tau, and QOP, which is K QIS dot T minus tau, and the overall solution will be the sum of these two. So Q0 will be equal to C to the power minus T by tau plus K QIS dot T minus tau. And then if you apply the initial condition, so at t equals to 0, Q0 will be equals to 0. So you will get t, you substitute 0. So 0 will be equals to C plus KQIS dot minus KQIS dot tau. So and then if you put that value of C in place of C, then you will get, so what is the value of C? So C will become this. So you will get KQIS dot tau to the power minus T by tau plus T minus tau. So equation 3.154 will be the output equation. It is very easy to derive. Hopefully all of you understand. If not, you can ask me. It's very easy to derive it. So now, so we see that now let us see the equation 3.154, and you see that the equation 3.154 at t equals to 0, Q0 is 0. Okay, because this is tau minus tau plus 0, which will be 0. So Q0 will be equals to 0. Now, as the t is increasing, Q0 is also gradually increasing. So for ramp input, the output is also some type of ramp, but there is something. Then can the output reach the input at steady state? So for that we need to calculate the error, and we need to know the steady state error. So we calculate the error. Again, the error is Ki minus Q0 by K, where the Ki will be equals to Qi, sorry. So Qi will be equals to Qis dot into P. We have seen that, and then Q0 by K will be equals to minus Qis dot tau, which is or minus Q by tau, minus Qis dot small t plus Qis dot tau, and then this Qis dot small t will be cancelled out. So ultimately we'll get Em will be equals to Qis dot minus Qis dot tau, Q or minus P by tau plus Qis dot tau. So Qis dot is constant, so you don't need to worry about that. So now you see that although that time t equals to 0, output equals to 0, and output will also increase as the time will go on increasing, but at the steady state, that means when t tends to infinity, you see that first term will die down. That means e to the power minus t by tau. So if t is infinity, so it is 1 by e to the power t by tau. So 1 by infinity, so it will become 0. So output will be equals to Qis dot into tau, because there is no t here. So what will be the output? What that will be the steady state error. So as t tends to infinity, it cannot reach the input. Always there will be error, and the steady state error will be Qis dot into tau. Now you see, what do you need? Tau need to be, so steady state error will be Qis dot into tau. So tau need to be less. So in order to get the steady state error less. So tau is basically here acting as a time lag. So what we learned, although for step input, the output of the first order system can reach then steady state, and the final error will be 0. But for ramp input, we cannot reach the input at steady state, and there will be a final error, or the error at t tends to infinity, or which we call as a steady state error, and which is be some constant into tau. And if your input is ramp, you want to decrease the steady state error, your tau should be less. So that's all about the ramp response. Now tell me if you have any query. Okay, nobody is asking anything. So with some pause, I can start again. Now ramp input is also covered. So now another thing is the frequency response of a fast order system. What is the meaning of the frequency response? So you need to understand it precisely. So as nobody is responding, I don't know how far you are understanding. Still, my duty is to speak and then tell properly. So the frequency response of the fast order instrument means, or any instrument, what does it mean? Try to listen carefully. Suppose you are giving some sinusoidal input, sine wave, okay, or the cos wave to any measurement system. Say having fast measurement system. So if you are giving a sinusoidal input to a linear time system, the output will also be a sinusoidal. So if you are in a LTI system, the output also be a sinusoidal. But if this output will be same as no, output will not be same as input, but output will also be sinusoidal. But the output amplitude will be different than input amplitude. Output phase will be different than the input. And so, so frequency of input sinusoidal, that is from very low to very high. So output also will be sinusoidal, but its amplitude will be different at different frequency of the input, and its phase will also be different at different frequency of the input. So it is very useful to plot the frequency versus the output input amplitude ratio and the frequency versus the angle or the phase angle, because you know, so now the input is, as the input is sinusoidal and output is also sinusoidal, so the nature of the output is immaterial because it will be sinusoidal. But then what if, which one is very much important? Important is the amplitude or the ratio of the amplitude, ratio of the output by input amplitude. That will be very important. So if the ratio is so important and the phase angle is so important, so it is important or it is useful rather than plotting the output, it is useful to plot frequency versus input output amplitude ratio and frequency versus phase angle. So if you can plot it, suppose you plot these two things, frequency versus amplitude ratio and frequency versus phase angle. So then if I ask that, okay, I gave some sinusoidal, then you will just ask me what will be the sinusoidal frequency, and from that frequency you have two charts. From the first chart you will find out what will be the amplitude, and from the next chart you will find out what will be the phase, and from there you can tell me, okay, you will get this output. For example, if you have a sine omega t as the input, the output will be a dash sine omega t plus phi. Now if you know the omega from the chart, you can, and know the amplitude from the chart, you can find out the amplitude a dash, and from the chart of the plot you can find out the phi. So you can tell me very precisely the output will be a dash sine omega t plus phi. So this is the beauty. And this type of plot or study is called the frequency response. That means with the frequency, how the output, how the amplitude ratio is changing, with the frequency, how the phase is changing. When that response you know, then you can easily tell me what will be the output response if you give some sinusoidal input. You have seen that it is very important for almost all the systems to know the frequency response, because now there is some extension of it. Suppose instead of giving uh, sinusoidal to a system, you can give some arbitrary input or some input which can be decomposed with many sinusoidal inputs. And for individual sinusoidal inputs, you know what will be the output, and then for that signal, the output will be the sum of all sinusoidal outputs. So if you know what the signal you are giving, you can decompose it with the Fourier series. You will get a series of sinusoids which is coming into the system, and for each sinusoid you know what will be the output, and you sum all the outputs and you give the user, okay, this will be the output. So this is the reason this frequency response is very important, and already you have read the frequency response uh, in electronics when you do the amplifier experiment in first year. There also you have studied the frequency response, and something you call the bandwidth also you studied. That means in which band of frequency it is not attenuating, and all those things you studied. So this is the basic concept of the frequency response, and this is the importance of the frequency response which we discuss in detail. Now let me see if you have any query, because this is a very important concept. Oh, still you don't have any query. Okay, very good. So now if we can write that Q0 will be equals to tau S plus 1 into Qi, and your S is, you can write as with the frequency j omega. So your Q0 by Qi, the j omega will be become K by j omega tau plus 1. And you can write it that K by square root of omega square tau square plus 1, and the angle is tan inverse minus omega tau. That means Q0 by Qi, the gain, what will be the gain of this transfer function? The gain of the transfer function will be K by omega square tau square plus 1 square root. And what will be the phase? Phase will be tan inverse minus omega tau. So now here you see that the amplitude ratio, what will be the amplitude ratio? A0 by AI. The amplitude ratio will be K by root over omega square tau square plus 1. And what will be the phase angle? That will be tan inverse minus omega tau. So now for zero order instrument, this is a first order instrument. So for zero order instrument, it is only constant gain. So what will be the phase angle? No phase angle, zero phase angle. And the output will be the same as the input phase. And what will be the gain? Gain will be K. It's very simple, and it does not carry much meaning. And it's obvious. And for first order, what will be the gain? Gain will be K by root over omega square tau square plus 1, and phase will be tan inverse minus omega tau. Now from the equation 3.158, you might see as the gain is K by something omega square tau square plus 1, and for any system, K is constant, tau is constant, input sinusoid frequency may vary. Now suppose input sinusoid frequency is high, omega is very high, then what will happen? The denominator will keep on increasing. When denominator will keep on increasing, what will happen? The gain A0 by AI will keep on decreasing. That means the input signal is going to be attenuated. So for a first order system, if you are giving in sinusoidal input frequency is very high, the output will be very less or very attenuated. So the first order instrument can act as a low pass filter, because high frequency component of the signal is going to be attenuated highly. So we can tell that the first order instrument behaves as a low pass filter. So for first order instrument, it is very important to know the corner frequency, that means beyond which you will get high attenuation, and your input signal should be, frequency of the input signal should be less than the corner frequency, so that output you will receive. Suppose you are using a first order instrument and you want to measure some signal whose frequency is quite high and more than the cutoff frequency, then if you use the same instrument, then you will not get any output and you cannot measure the input. So what you need to do? That instrument is not useful for measure such input of frequency high. So what you need to do? You need to modify the instrument or redesign the instrument in such a way that the corner frequency of the instrument should be more compared to the components of the input, frequency component of the input. Otherwise, you cannot measure the input signal. So that is the common sense. That's what bandwidth is very important. So bandwidth of the instrument. If your bandwidth of the instrument is low and your input frequencies components are more than your bandwidth, then you cannot measure it. You have to redesign the instrument so that your bandwidth become very high and you measure all the components because it will act as a low pass filter. Okay. So now let's see. This is a very important concept, and without board, I try to explain, and let's see whether you have any query or not, or you understood everything. Okay, so it seems you understood everything. Fine. So I wait for 1 or 2 minutes if you have any query. Okay, so you don't have any query. So this is the way we can think about. So every time, so if you see, so there are two aspects. One is time domain, one is frequency domain. Whenever you are taking an instrument, you have to analyze both. So if you don't analyze the frequency domain, that means what will be its bandwidth, what will be the cutoff frequency, what will be the corner frequency. If you do such, if you don't analyze, then you are using that instrument for all sort of inputs, then you may not get the measurement output for very high frequency component. So that you have to be very careful. So you have to be very careful while choosing the instrument. Both you need to know the time domain output and you need to know the frequency domain output and the frequency response. That means the omega versus gain and omega versus phase. And you need to be little bit knowledge about what may be the input frequency band of the input measurement. And if you have such idea and you know the bandwidth of the instrument, then you can properly judge whether that particular instrument of such and such bandwidth will be useful to measure the quantity of input which may have this much amount of input frequency. So this is very important. Otherwise, you will miss. You cannot measure the input properly. Okay. So that's all about it. So now its time is also ending. So now today we can end here, and next class will be on next Monday. We will keep on discussing, and you will keep on asking different questions and all those things to me. So for today, we can end the class here. Thank you, all of you, for attending the class, and all the best for this for the day.